Earth Science lecture on weathering and soils. First part of the lecture is on weathering, then we move to soils. Well, weathering is the physical, chemical, and biological breakdown of rocks and minerals. An example we'll use of weathering is looking at 5 different World Heritage sites. And we have a picture of a 12th century temple complex in Cambodia called Angkor Wat. And very few ancient structures are preserved at high latitudes with colder climates. Why might that be? Why are most of all these at not at low latitudes? In other words, in warm climates. That's something to think about as we go through this lecture. Here's an example of weathering in a cold climate. Notice what happens when ice gets inside a rock. It gets water in there, snow, and then it turns to ice. Ice expands and it pulls the rock apart and breaks it up in little bits. Or pushes the rock apart is a better way to say it. Plutarch, the Greek historian, said, "For water continually dropping will wear hard rocks hollow." Well, here's hard rocks with big hollow spots in them. These were originally volcanic rocks. And how did these holes develop? Why do they look like Swiss cheese? I think these are from Mozambique, I think. Well, rocks exposed at the Earth's surface were originally formed under different temperature pressure conditions, and weathering converts the minerals in those rocks to new minerals that are stable at the Earth's surface. So that's a good way to think about weathering in the big picture. The original rocks are stable at different temperature and pressures than we have on the Earth's surface now, and weathering converts them to new minerals and new minerals that are stable at today's superficial temperatures and pressures. World Heritage Sites, these 4 are deemed to be of outstanding value to humanity, but weathering just destroys them. Why do some rocks show more deterioration than others? Why do some rocks weather more than other rocks? Here's Machu Picchu. It's high in the Andes Mountains. Why is it particularly susceptible to weathering? And here's a 12th century mosque on the coast of Tanzania, Kilwa Kisiwani in Tanzania. What can be done to stop or slow down the natural processes that cause weathering to happen on these important structures? And here's an example of an important structure in weathering. Here's the Old Man of the Mountain, Live Free or Die, state of New Hampshire. It's on the quarter. That's what it looked like, but here's what it looks like in 2003. Those rocks are weathered. So if you go there today, you would not see Old Man of the Mountain because those rocks have all crashed in, weathered away. There's the original face. Weathering modifies the geological and cultural landscape around us. So here we have the Parthenon in Greece. It's 2,400 years old, and you can see that it's pretty weathered. It adds character to the structure, but air pollution, because it's in Athens, it really eats into that, into the rocks that make up the Parthenon. Disintegration of rocks and minerals into smaller pieces we call physical weathering. And there's 2 examples here that are important. One's called unloading and one's called wedging. Well, when erosion strips away overlying material, that decrease in overlying pressure lets the underlying rock expand upward, and when it does, it cracks in sheet joints, and those pressure release cracks expose the rocks, and then you can get freezing and thawing and water down in those cracks, and it starts to weather those rocks. Wedging is an example of where, like potholes in a city street, where water gets into those potholes and freezes and expands and forces the cracks apart. And as you get freezing and thawing, then you get bigger and bigger potholes, and rocks do the same thing as city streets. And we call that wedging. So unloading and wedging are 2 ways to disintegrate with physical weathering. So here we have an example of 2 different outcrops which one is pressure release cracks. Well, it's outcrop A. Outcrop B is a jointed granite and it's weathered along those joints. It's not pressure release cracks. One thing that's really important in physical weathering is surface area. And if you look at the bottom of the picture, you can see basically we have the same amount of rock, but if it's all one cube, you get 6 square meters of surface area. But you take that same rock and break it up into half a meter blocks, and you get 12 square meters. And break that up into 24 into quarter meter blocks, and you get 24 square meters. So that's a real important principle, because then you get physical weathering on 24 square meters of the same rock versus 6 square meters when it's one solid piece. An example of physical weathering is that picture there. It's a honeycomb weathering, and it's the result of salt crystal growth on the surface of a rock and expands the size of the hollows. And all kinds of interesting ways that you can get physical weathering. That's one of them. So here's an example from granite showing the same type of thing, where you get lots more surface area when it's broken. So here's physical weathering where you have granite breaking off in sheets from unloading. So the granite doesn't have as much pressure on it, so it breaks apart. Here's an example of physical weathering from Devil's Tower in northeast Wyoming. We showed a picture of that in a few lectures ago. And so you have these basalt columns that are hexagonal, and they break apart, and as they freeze and thaw and water gets in there and expands in this cold climate, it knocks them down, and eventually that thing will all physically weather away. So here's a question. Outcrops of granite are examined in Alaska. They are all at similar elevations. Some are located in the dry interior of the state, others along the Pacific coast. The granites have identical composition and textures. On the basis of the following information, which granite outcrop would weather the most rapidly? Well, the answer is number 1, because fractures soften up the rock and let water get into it, thus freezing and thawing and other physical weathering affects it. So along the coast, with fractures spaced 1 meter apart, versus along the coast no fractures, or in the interior where you have fractures, because there's more water and more surface area for physical weathering along the coast with the fractures present. Let's move from physical weathering to chemical weathering. Three processes that create chemical weathering are dissolution, hydrolysis, and oxidation. Well, dissolution is where minerals in a rock are dissolved by water. An example is that gravestone, that Madonna and Child. The acid rain has just removed all the details from that statue, and it was probably made of marble to start with. The acid rain just has eaten it up. Then hydrolysis is where hydrogen ions in water replace the other ions of silicate minerals. An example is when feldspar reacts with water, the hydrogen ions form clay. So you take feldspar, and feldspar reacts with water. The hydrogen ions replace the silicate, and so it gets to be soft. And that clay is an example of what we use with that clay is glossy magazine paper. So there's use for that clay. It's just not hard like feldspar. Oxidation is where oxygen reacts with iron and other compounds to form new mineral compounds. Rust in our car is that way, and you can see rust on that rock formation in the picture. Well, when minerals chemically weather, they can either have incongruent dissolution and oxidation, or they can have congruent dissolution. The difference between that is incongruent dissolution and oxidation produces clays and oxides. So, for example, potassium feldspar, that K feldspar, or actually all of these minerals would produce types of clays or real soft kind of minerals that would then be kind of part of soil. Whereas the minerals on the right, coarse calcite and halite, would totally dissolve in water. Here's an example of chemical weathering on, it's probably mica, and you start to see, or maybe it's a feldspar, anyway, you start to see different parts of that dissolving out incongruent. Here's a chemical formula. You don't need to know the formula, but it's just good to, you do need to know that feldspar will dissolve into into clay, and kaolinite is one type of clay. It's a white kind of clay, and you get all kinds of different clays that help form soil. It's a new solid phase plus dissolved ions. So the ions on the right under the red would dissolve and just go away, whereas what's under the blue arrow, the kaolinite, would be a new mineral. Here's pyroxene, chemically weathers into hematite, and the difference between that is pyroxene has an iron that's got a plus. It's an ion of +2, and when it weathers, it chemically weathers into an iron that's a +3. Here's an example of chemical weathering. The acid rain in the city has taken that lovely statue and just defaced it. The whole thing's just ruined. A sugar cube disappearing into a cup of coffee is an example of dissolution. Carbon dioxide is a small portion of the air we breathe, but when combined with rainwater, it creates a weak acid called carbonic acid. And actually that's carbonic acid, what's in Coke and other sodas as well. Well, carbonic acid can dissolve limestone and marble. Well, and limestone is common on the Earth's surface, and one reason we get caves like in northwest Arkansas is because limestone dissolves out when rainwater comes into that, and it dissolves the rock. All rocks have some cracks. Water going through the cracks is transported through the caves, and when it falls out into the caves and drips, it forms stalactites from the roof and stalagmites from the floor. The way I remember that is the tights hold tight to the roof, and so that way I can tell them apart. Stalactites and stalagmites. The sinkholes, and there's an example of a sinkhole on the right, would be limestone that dissolves in the ground underneath, even houses or something else, and then it collapses on down. If that was your property and your house, that would be very unfortunate. Here's an example of a cave and stalactites from the roof, and lake water inside a cave. And here's sinkholes. There's sinkholes all over that ground. And here's unfortunately a house that has caved into a sinkhole. Very unfortunate. You own the property and the house, and then boom, it's gone. And here's the process that would create a sinkhole. You have, maybe way down deep, you may not know that water's under there, under the rock, and your house may be on top of that. And then it slowly dissolves away the rock above it, and eventually the rock gets thin enough that it caves in. Here's a place where all the caves are around the U.S. The blue are limestone caves, the red are lava caves, the green are gypsum caves. Notice the green are like in western Kansas and northwest Texas and western Oklahoma. In fact, if you go to Medicine Lodge, right where that dot is, about in western Kansas, you can see gypsum all over the surface of the ground. It's really pretty. Another slide on chemical weathering. You might ask the question, where do you get hydrogen ions from so you can get hydrolysis? Well, the more hydrogen ions you get, the more rapid the chemical weathering. Well, the way you get it is by breaking down carbonic acid, and so when carbonic acid breaks down, you get an extra hydrogen ion coming off of that. And so when that happens, with hydrolysis, the silicates become weaker and more likely break down. Again, chemical weathering is what we're talking about. Here's some examples of acids and what we call pH. Low pH numbers are acidic, high pH numbers are alkaline. A pH of 7 is neutral, and it's a logarithmic scale, which means that each number is 10 times higher or lower than the number before it. So clear on the left, battery acid has a pH of between 0 and 1. Lemon juice has a pH of 2. Soft drinks have a pH of 3. Tomatoes have a pH of 4, and so that acid rain would have a pH between 2 and 4. Coffee has a pH of 5. Milk has a pH of 6. Water, pH of 7. Rains and streams. Rain and stream have some acidity, even if it's not acid rain, but they are slightly acidic. Seawater, on the other hand, is slightly alkaline. The dissolved minerals in seawater give it a pH around 8. Baking soda is 9. Soap is 10. Ammonia, household ammonia is 11. And oven cleaner has a pH between 13 and 14. Both battery acid and oven cleaner will really hurt you, but one's a strong alkaline and one's a strong acid. Acids and microbial activity can cause reactions with iron and other metals and rocks that can pollute streams. Acid rain drainage is real common in coal mining regions, and that's unfortunately real common in eastern Ohio and in Pennsylvania and eastern Kentucky. These coal mining areas have a lot of problems with acid mine drainage. Let's see what we've talked about so far, just kind of summarize that. Chemical weathering and physical weathering. Well, paint on a house gradually disappearing would be oxidation, and that'd be a type of chemical weathering. Sugar disappearing in hot coffee would be dissolution, and that'd be an example of chemical weathering. Bleach changing the color of clothes would be an example of oxidation, chemical weathering. Potholes on the road in winter would be an example of wedging. And nail polish removing nail polish would be an example of dissolution. Paperweight holding down a stack of bills would be an example of unloading. As soon as you take that weight off, that stack of bills is going to push up and be taller than it was when the weight was on it. Let's talk about a third type of weathering. We've talked about physical weathering and chemical weathering. Let's talk about biological weathering. And believe it or not, critters such as plants and animals can remove or break down rocks and minerals. And they can do it macroscopically by organisms we can see, or microscopically by organisms we cannot see with our naked eye. So we'll talk about some examples of those. Macroscopic biological weathering might include actions of plant roots, animal burrows, termites, other boring organisms. And microscopic biological weathering might be when a material is decomposed, it converts solid matter to gas with or without water. And it may also work on dead plant or animal matter. And examples of both those are sugar is dead plant material, May come from sugar cane or sugar beets or something else. And that combines with oxygen, and that weathers into carbon dioxide or water. Well, sugars are also in organic materials, such as apples have lots of sugar in them. And when that weathers, it forms carbon dioxide and methane gas. Here's an example of macroscopic weathering, because you can see the tree roots, and those roots are forcing the rocks apart. Those tree roots are forcing that rock apart as well. Here's an example of biological weathering by some animals, by people. And we've highly weathered that surface of that rock to make the pictures of the presidents that we see, the statues of the presidents we see there. So let's take our little graph again here and look at biological weathering with some examples. And groundhog digging a hole under your garage would be macroscopic. Fungus forming on a fallen tree in the woods would be macroscopic. Tree root pushing up a paving slab would be macroscopic. Compost rotting in your garbage can would be micro. What controls how quickly a rock weathers? Well, there's three things. One is rock composition, or what the rock's made of. One is the rock's properties, and the other one is climate. So let's look at each one of these. And you see a picture of a rock there on the left with low porosity. And because it's low porosity, water can't get into the rock. So weathering is restricted just to the outer rind. And so you see the brown weathered rind around the rock, and then the inside gray rock, and then a coin on it just for scale. And then you see weathering along fractures on the picture on the right. And that's granite, just because I can tell it's granite just because it weathers in rounded sheets, and because it weathers in rounded sheets like that because most of granite is quartz, and quartz, remember, it breaks in conchoidal fractures, which are round, so granite breaks in kind of rounded shapes like that. And you can kind of tell once you get used to the mineralogy and what's in a rock, what that rock is based on how it breaks just by looking at it. Same with limestone. Since it's mostly calcite, and calcite tends to break along cleavage fractures, it breaks a lot sharper than granite does. Let's consider composition as a variable in how fast a rock weathers. Weathering is faster in rocks composed of weaker material, or material that's easily converted to a weaker material. Feldspar is a good example, and feldspar converts to a clay. So it's faster in rocks that have lots of feldspar in them. Granite's an example. It has quartz, but it also has lots of feldspar in it. And so you get that conversion weakening the granite along those fracture points. Weathering is also faster in rocks made up of minerals that dissolve in water. Salt and gypsum are two examples of that. And weathering is slower in rocks of resistant materials. And quartz is example of a resistant material. So granite is interesting because it has lots of quartz and lots of feldspar in it. So those both speed up and slow down the weathering of granite. Okay, secondly, rock property is a variable on how fast a rock weathers. Weathering is faster in rocks that allow air and water in them. In other words, it's porous or fractured. Pores are spaces in a rock, and that space allows water to get in there. And if then that water freezes, it will push and break that rock up because water expands when it's frozen. Fractures are natural weathering surfaces, and so because a fracture weakens a rock at that point, it will weather faster along the fracture. And then igneous and metamorphic rocks generally have low porosity, and because they have low porosity, like we looked at that picture in the last slide, it's harder for water to get inside the rock, and so it doesn't weather as fast. Then climate is also a variable. Well, let's first of all define what a climate is. climate is a region's average annual temperature, precipitation, and vegetation. The climate is a region's average annual temperature, or affected by, probably is a better way to say it, a region's average annual temperature, precipitation, and vegetation. Well, chemical weathering is faster in warmer climates. So if you go down to the tropics, you're going to get chemical weathering. That's going to affect things more than in the northern climates. Physical weathering is more affects more things in the northern climates because of the freezing and thawing. There's more rain, more water, humidity, therefore more dissolution and hydrolysis in warmer climates. There's more shade provided by vegetation in some climates, which can impede evaporation and allow water to find its way into cracks and increase rates of weathering. Carbon dioxide is released from plants that combine with water to make carbonic acid. So the more vegetation you get, the more carbon dioxide is released, and therefore you can get some more carbonic acid. Then I'm down on point 5. Higher elevations may have more freeze and thaw cycles, so you get up in the mountains where you have more freezing and thawing, and you increase physical weathering. And extreme cold conditions, extreme cold regions like Antarctica don't have much thawing, therefore not much wedging occurs. And wedging, remember, is when you get water in a rock and then it freezes and then it wedges apart that rock because the frozen water expands. Let's look at this slide and just make a comment. Which of the following statements relates to the influence of weathering by rock composition, rock properties, or climate? Okay, first of all, rock exposed in the mountains of Alaska. Well, that's a cold climate, and so then it depends on the rock. So this is a climate question, and so it would be more physical weathering, less chemical weathering. Number 2, a lack of fractures in an outcrop. Well, that means that rock property doesn't have a place for water to get in there, so therefore it's a lower amount of weathering. Of course, that same outcrop could have lots of porosity, but we don't say anything about that, so that would decrease weathering. Okay, number 3, quartz is rarely affected by dissolution, hydrolysis, or oxidation. That's a rock composition, and therefore you don't get a lot of chemical weathering, as much chemical weathering where quartz is there. High porosity, a large amount of space between the rocks and the grain, that's a rock property, and high porosity would mean that water can get in there and therefore would increase weathering rates. Number 5, rocks on the coast of a tropical island. Well, tropical islands got a climate in the warm area, and also there's lots of water action along the coast, and so that would be climate. And then minerals that dissolve in the presence of water, well, that's the composition of the rock, so that would be something related to the composition there. If we go back to those World Heritage sites that we looked at the start of this lecture, we could analyze which of the 5 World Heritage sites have more potential for weathering, which would have less potential, based on those same 4 effects: rock composition, rock properties, and climate. So let's take each of these. The Parthenon, and well, let's take them from the top. Angkor Wat in Cambodia is in a tropical area, and lots of vegetation, lots of rainfall, so it would have a high ranking for lots of weathering. Kila Kisiwani in Tanzania, again, is in the tropical area, so it would have lots, and it's right on the coast, so it would have a high potential for weathering. Machu Picchu, way up in the mountains in Peru, it would have less weathering chemically, but would have quite a bit of weathering physically. I probably should have gone back and looked at the rock type for each of these. Sandstone in Cambodia, Angkor Wat sandstone, that would have lots of pores in it, so that would even increase the weathering. Kisiwani in Tanzania is limestone. It would have fractures. It wouldn't have as many pores, so it would not quite as have as much weathering as Angkor Wat. Also, there's not as much vegetation there. Machu Picchu in Peru is made of granite, and there's not much vegetation there, so it's not going to get a lot of weathering chemically, but it will get physical weathering from wedging and freezing and thawing. Mesa Verde in the U.S. is in a desert area, so not much vegetation. It's not in the tropics, so it's not going to have near as much weathering as some of the others. In Parthenon, Greece, the problem with that is it's made of marble, and marble is highly susceptible to chemical weathering, and so therefore it would there's acid rain in the city of, or potential for acid rain and pollution in the city of Athens, Greece. So I don't know what the answer on that, but I think probably I would put Angkor Wat at the highest potential perhaps, and Mesa Verde at the lowest potential, and then you could argue for the ones in between. We're going to change subjects starting with this slide and move from weathering to soil. Now, soil takes a long time to develop in an area, and soil combines the bedrock and vegetation and rotting plants and animals, and soil is critical to life on Earth, and God couldn't start creating plants and animals as we know them on Earth until he created soil. And so it's fun to think back in geologic time when he started creating soil. Not something we probably think about a lot. We probably just take soil for granted. But if we start losing soil, then we lose our agriculture. And if we look at Israel today, I'm not for sure, but I'm convinced that Israel at one time probably had a lot better soil than it does today. I have a feeling that goats probably ate the plants down to the roots, and it just never came back, and it's been experienced what's called desertification. So human activity and natural factors can affect soil, and I think today in Israel we see that. My father lived through the Dust Bowl in the early 30s when he was a little kid, and he tells about one time in Kansas when the whole sky was turned black because people had farmed western Kansas and West Texas and Oklahoma, and farmed land that they shouldn't have, and then we had a number of dry years, and that soil just went airborne. So the USDA, the U.S. Department of Agriculture, one of their big jobs is to help us as a nation here in the United States manage our soils and do it well and give advice on how to do our soils. So some of the information in this lecture has to do with information from the USDA and soil science. Well, how many components are there in the Earth system are contained in soil? Well, all four: geosphere, hydrosphere, atmosphere, and biosphere. Because soil is composed of regolith, or rocks and mineral fragments, water, air, and organic material. And you just don't get rich soil without organic material in it. And that's why we compost. It's important to do composting and then put composting in a garden, because that organic material is critical to a good soil. It's interesting to think about that, because without the death of plants and animals, you just don't get the kind of life that you get coming from soil. It's really important that God had put a system in place so that what we consider sad when something dies, God uses for his glory in creating rich soil for creating new life. Anyway, that's an interesting thought. Well, here's soils from different parts of the U.S. So let's think about these. What do we notice about them? Why do we think they look different? This is a get you thinking kind of slide. So what do you notice about these 4 different soils that we see there, and why do you think they look different? You may recognize some things about looking at this kind of a cut from where you live. Okay, so soil is a stratified mixture of regolith, i.e. weathered rock. Stratified mixture of regolith that includes enough organic material, water, and air to support plant life. That's an important definition. A stratified mixture of regolith, i.e. the bedrock's weathered, that includes enough organic material, water, and air to support plant life. Again, if you want to think about how long does it take to weather rock and create soil, it takes a long time. And it's not just, in some cases, a few thousand years. It's a long, long time. Okay, so let's look at what makes up soil then. Well, organic material is supplied by decaying plants and animals, and organics get mixed in the soil by burrowing animals, worms, insects. Water moves through the soil and leaches it. It dissolves iron out of the soil. Anytime you see a reddish orangish color in soil, it's because of iron in the soil. And water going through the soil can transport fine clay particles to lower layers, and so the clay particles actually moves in the soil from one part of the soil horizon to the next. And so we get into the next idea of what is a soil horizon. Well, there are horizontal layers in the soil, and what we just talked about creates those horizontal layers. There's organic activity, leaching and precipitation, and transportation of clay. In the United States, there's 12 major categories of soil in the classification system we use here. You're not required to know each of these, but it's important just as a general understanding that there are different types of soils and we can classify them. There's entisols, soils without layering, baritosols that contain expanding clays and layers mixture, inceptisols, young soils, poorly formed layering and weathering, aridosols, desert soils, saline and alkaline soils, mollisols, calcium-rich soils high in humus, spodosols, light gray, leached A horizon, organic material carried into the B horizon, and we'll talk about horizons in the soil in a little bit. Alphasols, acid soils with clay-rich subsoils. That's the kind of soil we have in my backyard where I live, and it doesn't make a very good garden either, because that clay binds up the soil and makes it really hard to grow something in it. Ultisols are more weathered alphasols, so that's what I need. I need more weathered alphasol in my backyard. Oxasols are intensely weathered and leached soils, and histosols are wetland soils, andisols are volcanic ash soils, and gelisols are permafrost soils. Each major division is subdivided into more specific categories, and there's 12,000 more specific categories. So I'm just pointing there again to the kind of soil that I'm used to in where I live. And I live in most of my life in eastern Kansas, eastern Oklahoma. So if we were going to take a soil science class and look at alphasols, we would be able to read through this paragraph as a description of an alphasol and understand what it meant. And we're not going to do that. I just wanted to show you the complexity of the science of what a soil scientist has to understand in order to be in their job. Like any job, there's a language and very specific information that you need to know in that field. Okay, let's look at soil horizons. This is important. You'll need to know this, and you'll need to understand each one of these soil horizons and quite a bit of information about them. So this is a key concept. You will need to know this. So let's look at O to start with, or the surface litter. that's where you get like the grass. Dead leaves, plants, animal remains, animals die, plants die, and it's usually at the top. Well, that's because that's where the people live, or animals live, and plants live. Right under that is what we call topsoil, and it's a dark organic area. It's mixed with mineral grains. It doesn't have as many fine particles and soluble ions. That's where the richness of the soil is. It was interesting when my parents lived in Iowa. They have feet of topsoil where they lived in central Iowa because glaciers had scraped topsoil off northern United States and Canada and dumped it into Iowa. And so they had feet and feet and feet of topsoil. Really good corn farmland because of that. Okay, right under the A layer is an E layer. It's a subsurface layer that has lost most of its minerals. And sometimes it's embedded in the A horizon or replaces the A horizon, depending on how much topsoil there is. Loss of topsoil is a real problem because when you get erosion, and we'll look more at erosion in another lecture, but that topsoil erodes, and it takes, like I said, a long time. And I can't give you a timing because it depends on the topsoil, depends on the climate, to create a good topsoil. But we can just lose it in a year, 2 years, very quickly. Okay, so there's the E layer, is a subsurface layer that has lost most of its minerals, and that's because it's leached out. Leaching water has moved through it, moved the minerals to another layer, and so you can see that it's kind of whitish and leached. Okay, the B layer, well, ions that have leached from A are precipitated there. It includes clay particles that were carried down from A. There's not much organic material there. There's oxidation, so it tends to be redder, and it tends to be bright orangey red in rainy areas, or in the part of Oklahoma between Tulsa and Oklahoma City is bright red. That's because of oxidation. And there's an accumulation of calcium carbonate in arid areas or in desert areas that forms a white layer. So the reason you get the E layer is because that's a part of the bottom part of A where it's leached out, and that those ions have leached down, and clays have leached down into B layer. Okay, then the C layer is above bedrock. It's the lowest layer, and it consists of soil parent material. Either weathered bedrock is what we call regolith, and you need to know what that word is, or unconsolidated sediments. So O, A, E, B, C. The most important layers there are A, B, and E, A, B, and C, and then bedrock down the bottom. But you need to know all these layers. Well, soil formation is controlled by the rock and the source area, temperature and the amount of rain in a region, climate factors, and biological activity occurring in the area. Well, how might soil formation differ on bare rock surfaces exposed in cold climates versus warm, wet climates? Well, in cold climates, soil may take thousands of years to develop into slow rates of chemical weathering. In warm, wet climates, soil may take a few hundred years owing to rapid chemical weathering. The thickest soil exists in tropical regions that have year-round warm temperatures and rainfall. So that's what I was talking about earlier. It just depends on where you are on Earth, and the climate depends on what kind of soil you get or how long it takes to develop a good soil. So soil formation is controlled again by the type of rock, the temperature and the amount of rain, and how much biological activity. You need to know those three things: type of rock, temperature, and rain, amount of rain, climate, and biological activity. In other words, how many plants and animals died, and whether or not they can rot there in the ground and help provide a source of nutrients to that soil. Soil fertility, let's talk a little bit about that. You don't have to have a thick soil to have a fertile soil, and fertility changes over time. Fertility is just an idea of just is the soil good enough to have plants be able to grow on it? So fertility changes over time depending on leaching and replacement of nutrients by weathering. Heavy rainfall can carry away nutrients, and it's something you get in a rainforest. As soon as rainforest is cut down to, say, plant farms, you're going to get really good soil for a year or two, and then the heavy rainfall will leach out the nutrients from that soil, and it will just be awful. So when they're cutting down rainforests in parts of the world, they're basically destroying the soil there after a couple years. And so what happens is they slash and burn because they're desperate to have somewhere to farm, and basically destroying the land or the soil's ability to have vegetation in the future when that happens. So there's thousands of types of soil, like we said earlier, and here's a map of the United States. And if you look at Arkansas, most of western Arkansas, it's an ultisol. If you look at Oklahoma, it's an alphasol or a mollisol. Let's take a piece of that U.S. map centered around the Kansas, Missouri, Arkansas, and Oklahoma area, and look at the soils that are most common in those states. First of all, the alphasol is an acid soil with clay-rich subsoil, and acid in soil is often related to how much clay is in that. And so you see that dark purple area is alphasol. And then a mollisol is a calcium-rich soil high in humus. And you see the gray area is a mollisol. And most of the Midwest is a mollisol, and that's one reason it's such a good breadbasket, and why Kansas has so much wheat, for example, because the state has really rich soil from the grasslands that have been there, created for a long time. Ultisol is a more weathered alphasol, and so we see the green ultisol in most of Arkansas. It's not a very good soil, it's because it's so weathered. And then in the inceptisol is a young soil, and you can see that going down through the Mississippi River Valley, and it's rich, but it's a young soil. Okay, so how does the climate affect soil profile? So if we go to look at the layers, we get A, B, and C, and then bedrock. We're skipping the E layer here because basically the E layer is where the A layer has leached out and moved stuff down to the B layer. You may not see much of an E layer in between A and B. Well, in an arid area, you get a thin topsoil, just very, very thin at the top, if any, and then calcium carbonate or caliche nodules under that, which it's just like drilling through a hard rock. It's hard, and then weathered bedrock, and then bedrock. So you notice that the A layer and the B layer are really thin, and the C layer is even thinner. And in a temperate area, you'd get a thicker A, B, and C layer with an O layer, because the O layer would be that grass and decayed vegetation at the top. Okay, so if we diagram that out, in an arid area, you get thin, mostly unweathered area, because infrequent rains leach upper layers and carry dissolved ions down a short distance. Down to the B layer, you get caliche formation there. Water evaporates, iron are left behind, and precipitates out and forms that caliche rock at the top of the B layer. So you're putting a fence post in where you live in an arid climate, you're going to get in the rock bar out and knock through that caliche layer to get through it. And here you see a caliche layer in an arid area. Okay, in a temperate climate, you get rich, thick humus. It's mildly leach, and in the B layer would be get minor precipitates. In a temperate area, you get a moderate rainfall. Rains leach upper layers and carry dissolved ions down. Some ions reach the groundwater, some precipitate out. And if they hit the groundwater, then those ions are moved out of the area. In a tropical climate, you get a thick soil, but you don't get much humus. And you get lots of leaching because there's lots of water that comes from frequent rains and soil. So ions are just leached right through that soil, and a lot of the fertility is leached on out. The B horizon's thin because the water moves the ions out of the area. So there's only really insoluble minerals left, which is why it's so dangerous to cut down the forest canopy in a tropical climate, or even for that matter to destroy the grassland and let goats eat it down to the roots, because the soil is not going to grow back. So there we see on that last arrow where the minerals are being leached away and groundwater is moving. Well, how is the thickness of soil in a region related to weathering? Well, the best answer here is B. Weathering increases the thickness of soil because it provides more materials to be incorporated into the soil. So weathering is critical for soil development. And A, why isn't A a good answer? Well, because weathering actually increases the thickness of soil. And why isn't the C a good answer? Well, regolith is directly related to weathering, so that's just a nonsense answer. Okay, from what you've learned about geologic time in Chapter 8, approximately when did the first regolith form on Earth? When did the first soils form? Well, that's a good question, because God couldn't create vegetation in abundance and then animals eat that vegetation until he created soil so that vegetation could grow on it. Well, regolith could not form until there's rock exposed to weathering, and soils needed biological materials, land plants. Therefore, the earliest regolith probably developed regularly early in Earth history. Regolith meaning the part of the soil that's derived from weathered rock. But it wasn't until the Silurian time that soils really developed, because that's when God started developing lots of land plants on the surface of the earth, on the continents. A little bit about soil erosion and conservation. I talked about conservation early in the soils discussion a few slides back. Well, soil can be depleted a lot faster than it can be formed. Soil erosion rates are affected by climate factors and land use practices. It's very, very important to be careful how we manage our topsoil, because it can just blow away or be moved away quickly by water very fast. Well, soil particles are detached from the soil column and transported away by rainfall, by water velocity, in other words, how fast the water is moving the soil away. And the character of soil. If there's lots of sand in it, it'll blow away quicker. If you remove the vegetation cover, the water and wind can blow that soil or move that soil out quicker. And if you got hills, the water runs down faster downhill, so it carries the soil away. At one time, farmers planted their rows up and downhill because it was easier to plow that way. The problem is then the water runs down down those rows and cuts a furrow and takes the soil with it. So one of the jobs that conservation agents have with the U.S. Department of Agriculture is to go give advice to farmers about how to manage their land so that they don't lose their soil. Let's develop this concept of soil erosion and things that help cause soil erosion issues. Well, look at the left picture. You see a raindrop hitting the ground, and notice that as soon as it hits, it splats and soil particles are dislodged. That's why if you stand in a mud and rain hits next to you, your shoes get all dirty because rain is hitting and moving the soil particles up and then getting your shoes muddy. Well, you get enough of that and pretty soon you get something like on the picture on the second from the left, and you get rivulets coming down through the land. That land was left bare. Probably shouldn't have been, but it was. And so you get channels carved on a plowed field. You can use a type of plowing that leaves vegetation at the top of the field, and it breaks that up so you don't have water being carried away, or water carrying soil away. It can really move a lot of soil off your land, and that you just don't get it back. It's gone. So it's very serious. And then the third picture from the left, you get wind erosion. Dust rises above the cultivated field, and dust just blows that soil away, and again, you don't get it back. You own the land, but now you just own poor soil, and that's really very unfortunate. And I mentioned the Great Dust Bowl, and you see the house being engulfed by a dust storm. My wife's grandmother used to tell the story. They lived in Meade, Kansas, that when her father was a baby in the crib, they had to put a damp sheet over his crib because the dust storm, dust would come right through the walls of the farmhouse, and there'd be coatings of dust over the baby, and they had to protect him. It's just very serious. And here you have a picture of erosion due to wind, which is the red dots, and water due to the blue dots. And each dot represents erosion of 200,000 tons of soil per year due to water or wind. Soil erosion is a real issue. Notice the white areas probably just don't have a lot of soil, and because they're kind of mountainous areas anyway, or they have a lot of vegetation, and that vegetation protects the soil from being eroded, or grass or trees, and the vegetation will keep soil from being eroded. So for example, eastern Oklahoma is mostly ranch land, so there's a lot of grass. It's not plowed, so you don't get a lot of erosion. Western Arkansas just doesn't have a lot of farmland, so you don't get a lot of erosion. Okay, humans are now more important as agents in moving soil and sediments than all other natural processes in the earth combined. We've been talking about this, but agriculture really can accelerate soil loss if you don't manage the land properly. Poor soil management causes really bad soil erosion, and today we have very sophisticated soil management in the United States, but in countries where we don't have that level of sophistication, where they're, say, in Latin American countries where they're slashing and burning rainforest, and then that rainforest just doesn't have a good topsoil, that poor land management will cause big problems. So the highest erosion rates are in guess where? Africa, South America, and Asia, where farming practices just are not well regulated and you get lots of rainfall. The lowest erosion rates are in Europe and North America, where governments encourage preservation of soils by good agriculture practices. So even in just a country like the US, the loss of soil erosion is tens of billions of dollars a year. So it's very serious, and it's important for you to know about, even if you aren't a farmer. You really need to understand the importance of good agriculture soil management. Here's a little graph. It shows on the left, on the vertical scale, the erosion billions of tons per year, and then different years by wind erosion or water erosion. And this would be in the United States, and so it's erosion rates of soil on U.S. cropland. And notice that erosion rates are going down over time mostly because the U.S. government has been paying farmers to not plow their land and put it in what's called CRP, or set aside land, and put grasses on their soil. And so just by not farming the land, we help preserve the soil here in the United States. And of course, I like that because it makes really good pheasant hunting too. Okay, so here's a little picture. Examine the graph. Which conditions are most likely to result in wind erosion of soil? Well, A, where you have high temperatures and low precipitation, in other words, desert kind of places. And water erosion, which conditions? Well, high temperatures and lots of water, lots of rain. If you think about wind erosion, you get that in a desert. And if you think about water erosion, you think about heavy rains and no freezing, so the water's not held back, and vegetation gets cut down, and the soil just runs off down with the water. Let's go ahead and summarize water and wind erosion just by doing some comparisons. And if we compare these different sentences, we can see that 2, 6, and 8 apply just to wind erosion, and 2 says that wind erosion occurs more wind erosion occurs in regions of warm, dry climates. And arid regions, number 6, arid regions experience this most often. And number 8, wind erosion can form sand dunes or dunes. They may be silt dunes, not just sand. And water, 7, 9, and 10, water erosion is expected in tropical regions, number 7. Number 9, it's prevalent east of the Mississippi. So most of the erosion that occurs in soil east of the Mississippi is from water erosion. And human modification of stream systems has a big effect on water erosion. So humans have a big impact on erosion in general. And then all the rest of the numbers, both wind erosion and water erosion, both wind and water both affect soil erosion for one, rate dependent on vegetation cover. They're both affected by moisture content of the surface. Velocity is important. The faster the wind and the water, the more soil's eroded away. Number 5, depends on soil type. If you get a soil with lots of vegetation in it, lots of humus, that will be affected differently than if you have a soil that is silty without a lot of vegetation. Wind can pick it up faster, for example. Number 11, a large temperature range. Depending on the temperature, if it's hot and dry, that will affect wind. If it's hot and very moist with lots of running water, obviously you get water erosion. So it depends on climate. So 11 and 12 are related. Again, in summary, let's take the different systems that affect Earth science and compare those to how they well, the exosphere, solar radiation can dry out soils to promote dust storms. And at the same time, what's on the Earth can affect solar radiation because dust storms can block out solar radiation. Basically, it just means that dust storms will block out sunlight. It's not that hard a concept. More sunlight dries out the dirt, and more dirt in the air blocks out sunlight. So that's A and B. C and D, atmosphere to hydrosphere. The carbon dioxide from the atmosphere adds rainwater to form acid rain, and so chemical weathering is slow in region with high evaporation rates. So both of those have to do with how the atmosphere and hydrosphere interrelate. Then on the right side, E and F, hydrosphere related to the biosphere. Pollution increases the acidity of rain. So the biosphere, i.e. people or animals too, create pollution. And then F, soils provide nutrients for plants. Or no, I mean F is plants take up water from the soil. So plants, the biosphere, take up water, i.e. the hydrosphere, out of the soil. Okay, G and H, how the biosphere relates to the geosphere. Soils provide nutrients for plants. Plants are biosphere, soil is geosphere. H, actions to limit the effects of weathering on heritage sites would be biosphere, i.e. people affecting the geosphere, the weathering of the rocks there. Agriculture results in soil erosion. People, again, the biosphere, create soil erosion. Immigrants inscribe names on rocks, i.e. You scratch your name on a rock somewhere, that's people affecting the geosphere. Organisms break apart rocks, like tree roots break apart a rock. The biosphere is affecting the geosphere. And then atmosphere and geosphere related to each other, I and J. Oxygen in the air, i.e. the atmosphere, reacts with iron in rocks to form iron oxides. So the oxygen in the air is affecting the geosphere, i.e. the rocks. And then J, winds carry fine materials eroded from soil. So wind picks up the geosphere, the soil. Basically, this is just kind of logical relationships between things. And so let's just keep going. K, some minerals dissolve in water. Dissolution forms caves. So that's where the hydrosphere, the water, is affecting the geosphere. So, and then, actually I got that backwards. That's where the geosphere, minerals, are getting put into the hydrosphere because the minerals from the rocks are going into the water. And then L is where water freezes and cracks to cause wedging, or in other words, hydrosphere, the water is affecting the rocks. Or minerals are precipitated out of the water. In other words, the water dries up and minerals are left somewhere. We looked at like a saline lake in a previous lecture. And then chemical reactions convert minerals, and that happens when the water is impacting the minerals. Okay, and the last two, M and N, the biosphere to the atmosphere. Biological weathering processes in the presence of oxygen are faster than anaerobic processes that occur without oxygen. In other words, oxygen has a big impact on weathering processes, and the atmosphere is where we get oxygen. Anaerobic just means no oxygen, or processes without oxygen. And then finally, N, plant roots release carbon dioxide. So the biosphere, plants, are putting carbon dioxide in the atmosphere.